Okay. So I do just want to spend time reviewing, talking about the different things on the exam. Also, just to let you know now that on Moodle, there will be a file, an Excel file that you can grab when you take your test. It won't be open until tomorrow, but you can grab it, and so you want to type in all the data that's on the exam. So you can just grab it. It's already in Excel for you. Okay. So I figured that would be helpful rather than having to type in. Especially since one of the problems has 60 data points, I figured you didn't want to type in 60 of them while you're on an exam. So
last test I messed up a couple inputs, I think.
That's another reason why I did it. So I figured that would make it easier. So so let's talk about what we did since the last test. So starting back in chapter 8, and this is would have been the stuff that I just sent you the email with the homework back. So in chapter 8, we had the goodness of fit tests. And in particular, we had the ones that you were given a data set does a particular distribution fit that data set. So we've done it for Poisson, we've done it for normal, we've done it for exponential, we've done it for gamma. Any of those would be fair game. So remember again, for the discrete distributions, typically you're given a number of observations, like for Poisson, you would be given number of observations number of times 0 occurrences happened, number of times 1 occurrence happened, 2 occurrences happened. You would need to calculate the mean and then use a Poisson distribution with that mean to figure out an expected number of occurrences of each of those, given how many ever trials there are, and then you would do your chi-square statistic like we've done, right? Observed minus expected squared divided by expected, and sum it up. We've also done the ones with a continuous distribution where you typically break it up into classes of equal probability. You did that on the homework that I sent back to you. You did it for normal, you did it for exponential, and you did it for gamma. All three, right? So make sure you can use those functions to get those boundary class points and be able to count the number of observations in your data set that fall into those classes and so on down the line. Remember, for your degrees of freedom, you always have to subtract 1 regardless, but then you also subtract the degree of freedom for each parameter you estimate. So, for example, for Poisson or for exponential, those are ones that we typically estimate 1 parameter, so you'd have to subtract off an extra degree of freedom for that. And for normal, usually you have to estimate your mean and your standard deviation, so you have to subtract off 2 for both of those. That all sound familiar?
So you said for discrete, it's the one that's like, this occurs so many times, this occurs so many times. And then continuous is the probability.
Is usually the probabilities, yeah. And then in 8.2, we did what was called the contingency tables, but we did the tests for independence of variables. So again, we constructed those contingency tables. So you have a table of observed values you construct a table of expected values, and you compute your chi-squared statistic. So just as a quick one, this is number 5 on page 425. Just talking about how we set those things up. So this is gender versus whether or not they care if people smoke in public. Oops, this is total. I think we've actually done this problem, but the idea behind independence is that in each of these particular entries in the table, you should be able to compute it by doing the probability of A intersect B equals probability of A times probability of B, right? So if this is my A, oops, if this is my A, why am I not writing on? If this is A and this is B, then my probability that A happens is the 503 out of the 1015, right? And the probability that if this is my B, the probability that B happens is 564 over 1015. So when you do that expected table, instead of that two, if you have male and favor, this number here should be, write it a little bit bigger. It should be 503 over 1015 times 564 over 1015 times 1015. If they're truly independent, you should be able to calculate the expected number in the intersection by calculating the probability of the intersection by multiplication and then times the total number. Right? That was the whole idea. Okay. And then, of course, these two numbers cancel each other out. So you really just have to do the 503 times the 564 over the 1015. And we did that in Excel. We did all that in Excel. Should I go through it in Excel again, or are you okay with it?
You take 564 times that.
The 564 times the 503. This one, you want to fix the row. Do an absolute cell reference on the row on this one. This one, you want to do an absolute cell reference on the column. This one, you want to do an absolute cell reference on both. And then you can copy and paste all the way through your whole table at that point. Because this number, you don't want it to change by column because it's stuck in that column, right? But you do want to change it when you go down a row. This one, I don't want it to change by row because it's stuck in that row, but I do want to change as I go across the column. So if this were, say this is row 2, this is row and column B, then this entry here would be, so this would be C, D, and E, and this would be 3 and 4. So then you would want to do, E2, but not change the E. you would want to multiply it by B4, but not change the 4. And you would want to divide it by E4 and not change either. That's what that would look like in that cell. And then you can copy and paste it to the rest of the spots. And then do your observed minus expected squared divided by expected, add it up. Same thing you would do in the previous part, previous problem, previous setup. That okay? Like I said, that was in your last homework. Let's see. And then we did 8.5, which was...
What number was that one?
That was 8.2. So we did 8.1, 8.5 was the tests about the median. And in particular, what I'm interested in is just the Wilcoxon sign test. Now, on the homework, there was some confusion between paired differences and checking the median versus having two distinct groups and wondering if one median is bigger than the other. Okay. So in the first problem that was on the homework that I gave back, that 8.5-5, that was a paired differences problem. You wanted to see, basically you wanted to see, did a student's GPA in the spring semester, is there any difference in the median versus the student's GPA in the fall semester? So it's same student going from fall to spring. So when you have a paired difference, like a before and after, you want to do this, you actually compute the differences and then check to see if the median is different from 0 or greater than 0 or less than 0, depending on the context. Okay. The other one is if you've got two different types of groups and you're trying to see if the medians are different. That's a different statistic where you have to remember the different expected value in the variance, and I'm not going to ask you that on the test. Okay. The only when it's a Wilcoxon sign test, I want you to use it where the expected value is 0 and the variance is the sum of the squares of the first n integers. So if W is your Wilcoxon statistic, the expected value is 0 and the variance is n times n plus 1 times 2n plus 1 over 6. That one. So if I give you two different or what looks like two different populations, it's going to be a paired differences one. You would definitely want to subtract and then check to see if the median is different from 0.
Can you say that again?
If I give you what looks like two populations, it's going to be a paired differences. So you would subtract and see if the median is different from 0. In that section, there were 3 different types of tests we talked about. I only care about the Wilcoxon sign test for this one. The other one was just the regular sign test, and it was a binomial probability. Is it how many positives, how many negatives you came up with the data set? And then checking to see if you've got too many positives or too many negatives. Is it above or below the median? Not worried about that. I'm just worried about the Wilcoxon sign test, where you have to rank them and sign them and add them up and that stuff. Okay. So then the last part that we talked about, we kind of jumped around some in the text. So let's just talk about specifically what I want you to know. So mainly, I wanted to talk about, no one wants GeoGebra open. What mainly wanted just to talk about different properties of estimators. So the bias of an estimator is the difference of the expected value of your estimator minus the true value. So an unbiased then would mean that your expected value of the estimator is equal to the theta. So if I give you an estimator, you should be able to tell me, is it biased or unbiased? Basically by taking its expected value and telling you if it equals the value you're looking for. Okay. Or, given an estimator, can you find a constant so that when you multiply by it, you get an unbiased estimator? And that, again, just find the expected value and multiply it by the appropriate constant that cancels out whatever constant you have out in front. As an example, remember when you do, if you use your theta hat, let's say that x is uniform on 0 to theta, and your theta hat is your maximum of x1 out to xn, then you can show that the expected value of theta is actually n over n plus 1 theta. So that is not unbiased. It's a biased estimator, right? But if you take the expected value of n plus 1 over n times theta hat, you get theta, right? So that's what I mean by find the constant that makes it an unbiased estimator. Does that make sense?
Where'd you get the n over n plus 1?
That is just what it is. I mean, you would have to go through the...
Oh. Okay.
Yeah.
I was like,
yeah.
That just got it.
You would have to get your PDF for your maximum of a random sample and then multiply it by x and then go through. You get that.
Yeah.
Is that okay for bias and unbiased? Okay. We also talked about consistent estimators. So remember, the definition for consistent is that the probability that the difference between theta hat and theta is less than epsilon when you take larger and larger sample sizes. That probability has to be 1. That's the definition for being consistent. But we had a nice criterion that said, well, if it satisfied a certain property, then we knew it was going to be consistent, and that had to do with the variance, right? So if the limit as n goes to infinity of the variance of theta hat is equal to 0, then theta hat is a consistent estimator for theta. Remember, for this, we also need that theta hat's unbiased. And then we also talked about efficient estimators. And really, we talked about relative efficiency. You look at the quotient of the two. That's the definition of relative efficiency. And if that ratio is less than 1, then which one's more efficient if the ratio is less than 1? If the ratio is less than 1, which one's more efficient? The top one is, right? Because that means the variance is smaller. Okay. So if it's greater than 1, then the bottom one's more efficient. So that's how you check relative. If I ask you about two estimators and ask you which one's more efficient, you want to calculate the variance of the two and see which one's bigger, essentially, or which one's smaller. The smaller one's the more efficient one, or calculate that ratio. Again, for these, you want the two estimators to be unbiased. We started talking about being the most efficient estimator that you can possibly be, or a minimum variance estimator, but that's not going to be able to save that for the final. Because we haven't done enough of the background yet to put it on the test anyway. So this covers basically what your test will be over. There's 6 questions on it. I'll tell you that. And like I said, the ones that have the data, there'll be an Excel file on Moodle you can just go grab. I mean, the data will also be on the test, but that way you won't have to type it up. Unless you really, really want to.
So for the paired difference one where you subtract it, you just do that, like the x minus the y?
Yep.
And then rank those?
So, yeah, so if you had, what was that one, 8.5-5?
Yeah.
All right, so here was the data for that problem. So the first thing you would do is grab the keyboard. Yeah, so the first thing you would do is take the difference of those two. And then I'll do the absolute value of those things. So I want to do the rank. And we'll always use the rank average because we're going to average any ties. Do the rank average of each of them relative to the rest of the array. And then we want to do ascending order, so we'll change that to 1. And then I want to multiply it by the sign of the difference over here. So I want to rank the absolute, I want to rank the distances. That's why I took the absolute value, right? How far away from the median it is. But I want to sign them by above and below. So that should give me what I want for the ranks. So there's our ranks. And in this case, since we're doing paired differences, I want to know, is the median, does it appear that the median is, well, bigger in this case than 0, it looks like, because there's definitely more positives than negatives. But again, we'll want to compute the sum of this that's our Wilcoxon statistic, is the sum of those things. And then you would calculate, let's do normal distribution here. This is the x value. The mean is 0. And the standard deviation is the square root of, what are there, 15? So it'd be 15 times 16 times 31 over 6. And I want cumulative. And if I'm doing a p-value, I actually want 1 minus that, since I'm looking at the one-tailed test above. Right? If I want p-value, I need to go above the 54, the probability that we're greater than 54. The normal distribution will give me cumulative up until that point, so I need to subtract it from 1. And the square root of 15 times 16 times 31 over 6 is that n times n plus 1 times 2n plus 1 over 6. So there's the p-value.
Why'd you do the 1 minus again?
Because I'm doing a right tail. I want the probability that was above 54. And the normal distribution is giving me the probability up until 54. So I need to do 1 minus to get the p-value that I want. So since my p-value is above 0.05, if I'm looking at 0.05 significance level, then I would not reject here. So that's how we would handle paired differences. We do the subtractions first and then just check the median against 0. Is that okay? Any other questions at all? Yeah, Joe.
On Friday,
You can take it Friday. Yep.
What time?
Pretty much whenever. Then you want to take it on Friday.
When you get home.
Well, if I'm not here, I'm going to leave them out on the table. So there's no classes are going on anyway. I probably will be here Friday, but I don't know 100% that I will be here Friday.
Where do we come
Just slide it under my door. And if you got the stuff in Excel, you can just email me the Excel sheet. Which I assume there'll be some stuff in Excel, so I would anticipate that you'll be able to do the stuff. Yeah. Email me the Excel sheet. Is anybody planning on taking it tomorrow? Are you?
Afternoon.
Afternoon, Rico? Yeah, that's an easy time to start you. Any other questions? Everybody's so quiet. Did I just make people sad? I don't think it'll be unexpected. I mean, if you're comfortable with what we just talked about, I think it'll be fine. Sydney.
So for the ones like this, that's the only type of one we'll have. We don't have the other one where it's you compare 60 medians are equal or something like that.
Yeah, we know. I will do that. Mainly because I don't want you to have to memorize the extra formulas.
Yeah.
I know that didn't sound like me, but.
So the homework problems we did, they're going to be similar to that.
Yes.
Basically.
Yep. Yeah, Joe.
How was your Easter?
It was good. I went to Minnesota, so I had a good Easter.
Any snow?
There was some snow on the ground still in piles, but because the week before they had like 10 inches of snow,
Yeah.
and then it got up to 60. So it's weird. But, yeah, it was nice. I had a good time. Enjoyed the lake. I always enjoy it. Nah, I don't. I'm not a fisherman. walked around the lake, saw the chunks of ice still floating on it. It was kind of cool. Any other questions at all? Because I assume you don't want me to start new stuff. No, then I won't start anything new.
Was there like some book questions you could give us for the stuff we haven't had homework on?
That extra sheet that I gave you.
This one?
Yeah,
Okay.
that'd be the ones I would look at. And then there were some in that other packet too that I gave you. I think that was on bias and stuff. I think in that one there are some in there. I can look at it again and see if there's some specific ones, but
Okay.
that'd be the ones I would look at for that. Mainly because the book questions started off with a little bit more complicated than what I wanted to start with, so that was why I did it in a little bit different order. That it? Yeah? All right. I'm good. If you're good, I'm good.